the plane, sort of the complex plane. So A plus BI, and you call this is a real part, and B called imaginary part. And then this is the real axis, the imaginary axis, just like here. Coordinate A, and here the coordinate B, and just express as a point on the plane. And this idea comes back to the I think first introduced this concept by Wessel. He's not a mathematician. I think he's some engineer in Norway in the late 18th century. He wrote some paper, but nobody took care of the paper, so it was forgotten. And later, Gauss used this. I don't know when he published it. Anyway, but Gauss, in his thesis, written by 1799, he used this complex plane to prove the fundamental theorem of algebra, and also Aragon. I think he's a mathematician in Swiss, and also he used the notion of the complex plane. And I think usually the French people use Aragon planes, and German mathematicians use Gauss plane. And then, if you express these complex numbers as a point on the complex plane, then it's very nicely express this number using the polar coordinate. So, so this is actually the point of AB. And we introduce the absolute value of these complex numbers. It's just A squared, square root of A squared plus B squared. So this is just the length of this lines. And if you introduce the angle from real axis, positive real axis to this point, then you can express this complex number as L times sinus theta plus I sinus theta. So this is a very interesting way to express because if you have two complex numbers, and okay, like this, Z prime, and if you have the product of these complex numbers, then if you use addition theorem of trigonometric functions, then you can easily show that this is so. So if you take the product of two complex numbers, then this angle is just a sum, and the absolute value is just a product. So this is, in a sense, quite powerful tool. Because, for example, if we want to solve the equation g to n equal 1, we can easily solve the equation. Oh, sorry, but before, I should go back. Sorry, I went too early, fast. Sorry. So, a simple application is so-called Domable's formula. So you take the nth power of cosinus theta plus I sinus theta, then you get n theta plus sinus n theta. So in this way, you can easily solve that, this equation. Because first of all, if this equation can solve, then its absolute value should be always this way. So that means absolute value is a positive number, so it should be 1. Okay. So z and this L should be 1. Therefore, you can just use this formula. Then this should be 1. Okay. Then only possibility is sinus and theta is 1 and sinus. This way. Therefore, you get what you get. And theta should be some integral multiple of the 2 pi. Therefore, theta is 2 pi n. So this gives you the very beautiful pictures. Of the complex plane. So this is 2 pi n and so on. So if you can draw the regular element inscribed in the unit circle this way. Therefore, if in the simplest case is n equals 3, so you have what you get is so this triangles, and this number is 2 pi 3 plus pi. And another way to write down is -1. I forgot. That's correct. Okay. And this is our omega I wrote beforehand, and this is omega square is -1 minus. So in this way, you can use the very nicely the complex numbers. Okay. Okay. So maybe I got too fast. But also there is a very interesting mistakes which Leibniz did. I talk about that. And then coming back to the again that's complex numbers. So I think that 1972 or something. Yes, the Leibniz wrote a paper claiming that x or 2 plus a fourth is irreducible. You cannot factorize into two polynomials of real coefficient. And the reason what he wrote is, first you can factorize using the complex numbers. Yeah, of course. Okay. Then, again, try to factorize this. Then, of course, what you get is x plus a So he wrote in this way. And he then added it's impossible if you say.
You missed a minus.
Where's
In
the
the
minus?
second bracket.
Oh, yeah, sorry, thank you. This is minus I. And then he claimed that looking at this formula, it's impossible to express this as a sort of a real polynomials. But of course, that you know that this you can easily factorize because first, and then of course, then we have to so everything is a real coefficient. So what is why is that the Leibniz did mistake? The point is he didn't know that square root of minus I or square root of I can be expressed as complex numbers. Strange enough, but even such a great mathematician did mistake. So what is this number? How we can find the square root of I, for example? So one possibility is just using this expression, what I said, I used. So if you use a complex plane, again, so square root of I means that if you multiply the same number, it becomes I. And then one possibility is, and also the absolute value of this is always 1. So this is what here. And if if you write, therefore,